Is that better? Yeah. Cool. All right. So something really cool. Goedel's incompleteness theorems are considered some of the most important and famous theorems derived by people in math. What it goes back to is at the turn of the 20th century, a German mathematician named David Hilbert published a list of 23 problems. It was like the first BuzzFeed list. 23 problems that, if solved, will change society. And this list of problems is still, some of them are unsolved, some of them are solved, and some of them have been deemed unanswerable. Our focus today is on Hilbert's second problem. Hilbert's second problem says, prove that the axioms of arithmetic are consistent. That is, that you cannot prove a contradiction from the axioms of arithmetic. So as mathematics became more abstract in the 1800s, you couldn't use English to convince people anymore. There's too much ambiguity in it. And so mathematicians started formalizing everything. And there was a hope that if you formalized enough, you could prove anything you wanted. And that everything that you proved would be consistent, and anything that you can write could be either proved or disproved. And then in the 1930s, Austrian mathematician named Kurt Gödel came along, and he believed in Hilbert. He completely agreed, and he tried his best to prove Hilbert's second problem correct, right, that arithmetic is consistent. Unfortunately, he didn't succeed, and what he proved instead shows that it's impossible to show that arithmetic is consistent within arithmetic. As a brief outline, well, first off, if you guys want to follow along, that's a URL with a write-up of all of this stuff. It goes more in depth than I will be able to. It's around 10 pages long. It's good.gl VGFRXO. V, F, and X are capitalized. Goo.gl, that's a URL shortening tool. So as a brief outline, we're going to talk about some preliminaries in order to understand Gödel's theorems, and then we're going to talk about some formal languages, then we're going to talk about the theorems. So the first thing is, what does it mean to prove something? Does anyone have a statement they want to say about what it means to prove something?
Like starting off with something that's established and coming up with what we want to prove.
Exactly. And so let's begin with a proof and sort of talk about its validity. Is everyone familiar with the fundamental theorem of arithmetic that prime factorizations are unique? Some people have seen it. I'm not sure everyone has. It goes like this. Is everyone familiar with the prime factorization of something? Okay. So if we want to show that prime factorizations are unique, the way it was proved is contradiction. So let S be the smallest smallest number with at least 2 prime factorizations. So is that easier to read, or am I still okay? Smallest positive integer with 2 plus prime factorizations. So we can say S is equal to P1, P2, and so on up till Pm. And it's also equal to Q1, Q2, up till Qn. Right? So S is the smallest integer with at least 2 prime factorizations. Now the first thing we can tell is that, let's suppose that one of these PMs, there's some PI, that's equal to some qj, right? That is, there's some number in common with these two factorizations. In that case, we can remove that number, and then we've got a smaller than s over pi has 2 plus prime factorizations. Right? So if s over pi has 2 plus prime factorizations, well then s is not the smallest. And so that's a contradiction, and therefore we know that all of these primes are different, that p1 through pm have nothing in common with q1 through qn. Then without loss of generality, we can say p1 is less than q1, because if it was the other way around, we can just swap the two factorizations. So if p1 is less than q1, then we might be able to write, let's say we choose a number t. Well, we define t to be s minus p1 times q2 to qn. That's a weird thing to do, but suppose we do it.
Are P1 to PM and Q1 to QN ordered?
Prime. Ordered?
Yeah, so is it lowest to highest prime or does
Order
it
doesn't matter.
Okay.
They're just, and you can have repeats too. So you could have 2 squared. So if we set t to s1, s minus this statement, right? Well, then that's equal to, well, if we use this definition of s, right, then we have p1 common. So I can factor out a p1, and we get p2 to pm minus q2 to qn, right? If we use this definition of s. And if we use the other definition of s, well, then we have q2 to qn common. And so we can get q2 minus p1 times q1 minus p1, q2 to qn. Sounds good? So then we know that t is smaller than s, so we just subtracted something from it. So t has only one prime factorization, which means all of these primes right here, they show up in the prime factorization of t. And also this prime right here has to show up in the prime factorization of t. So in that case, let's say that this has a prime factorization r1, r2, and so on up to rh. And then this thing is going to be equal to q2 to qn, right? So if this is the prime factorization of s, we know that p1 has to appear somewhere in the prime factorization of s, right? So here's a question. Can p1 appear in q2 to qn? No. Why not? It can't appear because q2 to qn are prime, and p is not equal to q2 to qn. P1 is not. And so one of these must be p1, somewhere in there. Right? So what we're saying is that this q1 minus p1 is divisible by p1. So we can write p1 times some number k is equal to q1 minus p1. And then from this we can write that p1 times k plus 1 is equal to q1. However, what do we know about q1? q1 is prime. And yet we've found a factor, two things that multiply together. They're both integer, that multiply together and get us q1. And so in both cases, we have a contradiction. And therefore, we know that prime factorizations are unique, right? You could draw a box. So does this count as a proof? Sure. Does this count as a formal proof? Sorry?
Of that statement, you mean?
Yeah. That's true. So it turns out that this proof doesn't count as a formal proof in the way that I'm going to define a formal proof. Actually, what this counts as is a semi-formal proof. Because what happens is that these statements that we wrote in English have formalizations behind them. And so therefore, it's a proof that mathematicians are willing to accept, but a computer might not. So in that case, what's a formal proof, right? That's the key question. And the way we answer that question is we start with a formal language. We've been learning formal languages in class most of the semester. And a formal language is simply exactly the same way we've been talking about formal languages. It's a set of symbols and a grammar that tells us which of the possible strings that can come from this language come from this alphabet is part of the language. So we can do some quick examples. I think we're all fairly comfortable with coming up with context-free grammars of things. So we won't do the grammar part. But let's just sort of talk about the formal languages behind mathematics, right? So if we're talking about a formal language for logic, what should our alphabet look like? Just shout out. Yeah. So and, not, or, and because we like syntactic sugar, we add implies and we also want, so those are our connectives. We also have constants, right? True and false. And we have variables, x, and predicates, which can take in a variable. That's a monadic predicate, meaning it takes in just one. I don't think we need something more complex than that. And of course, for all and there exists. Is everyone familiar with for all and there exists? Right, okay. And parentheses. This is all part of our alphabet, right? So in that case, we can say that some strings are valid, right? Quite quickly, we could say P or Q, is that a valid string in our language? How about P or? No, it's not. Let's do the same thing with arithmetic, right? We could have symbols for arithmetic. Arithmetic will build on these symbols for logic. We'll take all of these and then add some, because in the end, we still need to say things, make statements. And if we were talking about the truth or falseness of a statement, we need logic to be there. So what should we add to this to get arithmetic? The same things, right? Go ahead. Sorry? Yeah, so let's start with the simple stuff first, though. Plus, minus, times, and division. And yeah, order, quality, right? And then we should also probably add our digits, 0 through 9. Those are useful occasionally. And then we can add less than or equal to sugar, and we need more variables, different variables, variables representing numbers instead of variables representing Booleans. In fact, we probably want to take these Boolean variables away. And also we want functions, right? We could do a simple monadic function that takes in one variable. So then this would give us arithmetic. So then a question becomes, what can we write with arithmetic? So, for example, does anyone know how to write x is even in arithmetic formally? So that would be written as there exists a y such that 2y equals x, right? That would be x is even. How about x is prime?
But y has For to all belong
x,
to a
right?
specific set.
Sorry?
Or all x.
Sorry, just a second.
So I meant to say that y should belong to integers.
Yeah,
Should be
and
defined somewhere.
if we do that, then we have to add set theory to this as well. And the relations for set theory, we could say we're just talking about a set of symbols that are going
Okay,
from
so a symbol is
So
even.
we're kind of having an implied z in all of these because we're not talking about sets other than the integers. But we could, and you'd be correct. So yeah, normally when people talk about existence, we talk about the real numbers, right? And so we're used to real numbers, and so that would be true for any number. However, we're restricting ourselves to the integers right now for our arithmetic. So what we need is primes. So if we want to say y is prime, we say for all x, and if we want to say x is prime, we say for all y and z, either, so if y is less than z and yz equals x, then, sorry? Exactly. Y equals 1 and z equals x. So that's prime numbers. We're all comfortable with this stuff, right? So then here's a question. Is 1 equal to 0 valid in our language? Anyone want to say something?
Well formed, it's not.
It is valid in the language. It's not valid in, it's false in arithmetic, right? But it's certainly, based on whatever grammar we write, 1 equals 0 is something you could write down. So that brings us to the next section of formal systems. What is it that we need to add to a language in order to prove something? Axioms. Exactly. So that gets us to our definition of a formal system. A formal system is a language and a set of axioms, A1, A2, and so on. So I guess I should say it's a, yeah, so it's a language and a set of axioms. Yes? Are you going to ask about the turnstile operator?
No. I was
Okay.
going to ask, since you wrote it out that way, does your set of axioms have to be finite?
I was going to say, so logic doesn't have, I think I should just do that for safety. Because you're right that logic has a lot of axioms sometimes. And really when we start talking about
Still have to have finite
sets
axioms.
of axioms,
How can it have
You have
more
a variable
than
rate
finite?
axioms, you don't have a like.
if I have a variable in my axiom, so let's start talking about some of these axioms, and then we'll get exactly to that question. How can you have more than a finite number of axioms? So what are the axioms of arithmetic? Or I guess we should start with the axioms of logic first. Yeah. What are some of the axioms of logic? What should count as an axiom? That is, what is this kind of statement that we can't prove? Now, I actually had a lot of trouble finding this because very often people don't start with the axioms of logic. They start with a set of statements that people are willing to accept. That is, so there's this idea that your axioms should be the minimum necessary in order to prove what you're saying. And people, instead of that, go for the set, like a set of axioms in logic, because if you go to that extent, then it becomes hard to read, right? This is also why people use the implies operators. So one axiom we could write is, well, let's do it like this. For Gödel's proof, there's a couple of theorems that are valuable in Boolean logic. Now, I'll write those theorems down, and then we can talk about which ones we should consider axioms and which ones we should say they come from the other ones. So the first one is double negation. So if you've got a statement, not x, well, oh, by the way, this operator right here, the turnstile that I've been using, basically says the following formula is a theorem. So if, so not x implies x is a theorem, right? We're willing to accept this usually. So this is where we start to talk. You asked about how you can have an infinite number of axioms. There's actually an infinite number of axioms right there. And the reason is that this predicate x can be replaced with anything. So when we write not x, we're actually saying there's a lot of, if we stick to first order predicates with just a variable x, right, then we would have an infinite number of statements that this axiom handles. So if you have quantifications over those statements, then you are in second order logic and not in first order logic.
But to a computer can understand that axiom.
Certainly.
Like, it doesn't require that you enumerate all instances of
That's
statements.
true. So that's why we're okay with an infinite number of axioms, right? Because if you had an infinite number of axioms that you couldn't loop through, then you'd have a problem. So it's gray, I think.
You pick yourself in the second order logic when you
Yeah?
axioms. But that's kind of irrelevant.
All right. Sounds good. Well, so another axiom, or another theorem that we'll be using is trivial implication. That is, if x implies that not x implies. Call this. Then there's the distributive property over implications. So if you've got x implies y implies z, then that implies that x implies y implies x implies z. X implies not y. Actually, I wrote this wrong. Parentheses go here. There. So if this one states that if X implies not Y is a theorem, then Y implies not X is a theorem. Are you guys familiar with the contrapositive? That's what this is. So CP. And you can prove X implies Y. So if this is a theorem, then if X is a theorem, then Y is a theorem.
Explain again, I'm sorry, the second axiom there, I'm not sure I understand.
This one?
Yeah.
X implies, not X implies Y. So it's, so in the case that X holds, then not X implies Y trivially holds, right? Because not X is false. And false implies anything. Are you familiar with that definition of implication?
That's the explosion principle.
Yeah. And then if X doesn't hold, then the implication is immediately true, right? If you start with something that's false, you can derive anything. Are you familiar with that?
You could mechanically see that also. X implies Y is not of X or Y.
X implies Y is not of X or Y. Right, and then you just rewrite that and it turns out to be true.
Another way to say it is, if I can say if unicorns can exist, then I'm king of the world, right? And as long as unicorns don't exist, that's a true statement. Yeah. So, okay, where was I? All right, so this is called modus ponens. Basically, if you can show that X implies Y, if there's a theorem that X implies Y, and then you can show that X holds, then you can chain these two theorems together and show that Y holds. And then the last one is you can show X implies Y. And you can show Y implies Z. Then you can show X implies Z. This is called hypothetical syllogism. Basically, it's kind of like if you can show that X implies Y, and then that Y implies Z, then of course X implies Y implies Z, and so X implies Z. It's the, I think, transitive property. Yeah. So these are the axioms, these are the theorems we'll be using in order to prove Goedels Incompleteness. So comes the question, which of these should we consider axioms? Now, the easiest thing we could do is say consider them all as axioms, because that is legal, right? You can have more axioms than necessary. It turns out that really we only need these middle four if you rewrite them a little bit. The ideas are the same. You still need this implications get trivially true. You still need this distribution of an implication. You still need contrapositive, and you still need modus ponens, but the others can be derived from it. Sounds good? And likewise, we can come up with axioms for arithmetic. If I had more time, I would have liked to show you guys piano arithmetic and Robinson arithmetic. Those are two formalizations of arithmetic. Unfortunately, Goedel's Incompleteness will take a little while.
In like a sentence, what's Robinson arithmetic?
Yeah. I guess I should start with piano, just in case. So piano arithmetic says that it basically defines plus and times, from which you can define division and things like that, or divisibility, not division. And it also talks about this idea. It formalizes the basic things you do when you're trying to prove things in arithmetic. There is one thing added to piano arithmetic, which is induction. So induction has a special-looking formula. It looks like P of 0, and I shouldn't write there. So if you've got a predicate P, right, and you can show that that predicate holds for 0, and you can show that that predicate holds, that if the predicate holds for x, for all x, you can show that P of x implies P of, so the axioms for arithmetic have this idea of the successor to a number. That is, it's the number after. So S of 0 is 1. So S0 is 1 is equal to S0. 2 is equal to S1, which is just S0. Basically, you're applying this operation to get the next number. The cool thing about this is you can use this to define addition. You can use this to define multiplication. And so this is heavily used throughout the piano axioms. For induction, we say P of x implies P of Sx. That is, if you can show something holds for the 0th term, and for every term you can show that if it holds for the current term, it'll hold for the next term, well, then you've shown, I need another pair of parentheses, that for all x, P of x, then you've shown it for all of them. Induction. So this is what is the novel thing about the piano axioms. And the Robinson axioms take that away. They say, instead of that, we're just going to say no induction. But what they give instead is the statement that for all your numbers, either your number is 0 or there exists a number such that the next number after this number is your number. So this basically says that there's this order to the integers without needing to say, so if you have induction, then you can prove that there's an order using successors. You can define the order. Whereas this just creates the order without needing induction.
Same.
They're both.
There are
Look
things.
at that, those are just two different forms of induction, right?
This isn't. So this is limited to just describing the integers, right? This lets you talk about predicates. So there are things you can prove in general using induction that you can prove in the specific case with Robinson arithmetic. You can.
So Robinson arithmetic is slightly stronger.
When you say stronger, I think narrower is what I agree to, yeah. Okay, sounds good? So under piano or Robinson arithmetic, we'll be talking about Goedel's Incompleteness theorems. So the next piece will be a sketch of the proof. So how did Goedel go? We just talked about formal proofs, right? But we talked about our formal proofs in English, which means we can't yet prove things about proving things. And this is where Goedel comes in, because Goedel was looking for a way to talk about proofs themselves within mathematical systems, right? So Gödel had two theorems. Gödel's first theorem roughly states that any formal system containing arithmetic, that is, it's got multiplication and addition and divisibility, in any formal system containing arithmetic, there is a true statement that can be neither proven nor disproven. Okay? So, and then and the way you say that is the system is incomplete, is how you describe it.
You see, a true statement, you mean, how does he?
A statement. So logic, given a predicate, we know from a logical perspective that it's either true or false, right? Which means either P is true or not P is true. That's known as the law of the excluded middle, right? So if something is true, the question comes, can you prove that it's true, right? Truth and proof are separate things. It's hard to talk about whether something is true, and it transitions really nicely because, so Gödel reached these two theorems by starting with the liar paradox. Are you guys familiar with the liar paradox? It basically goes like this. This statement is false. That statement in English is neither true nor false, right? So if you can manage to formalize the liar paradox, that is, write the liar paradox inside your language, then you have just written something that is neither true nor false. Now that's much more dangerous than what Gödel's proof shows, because neither true nor false, that invalidates every proof by contradiction. Gödel did not do this. What he did instead was he came very close to the liar paradox. What he wrote was the statement, this sentence is not provable. Right? It's very close to the sentence, this sentence is not false. It just talks about provability instead of truth. And so when Gödel wrote, this statement is not provable, then you sort of get into this ability to talk about sentences that are neither provable true nor provable false, even though the statement itself might be true or false. Does that make sense? Kind of? It is weird. And then Gödel's second theorem states that in any formal system containing arithmetic, you won't be able to prove that that system is consistent. That is, proving a system is consistent basically means that proving that you cannot reach a contradiction. And on any system with arithmetic, you can't prove that this holds within the system. So let's get there. The sketch of the proof, go ahead.
Sorry, so if he's saying that any system containing arithmetic can be proven consistent, is he saying then that you can't know whether any of the work you've done in that system is valid or not?
Well, it's a little bit more complicated than that, I think, because of a couple of things. One is that, so yes, you can't know that it is consistent, but I think in our experience, arithmetic tends to be consistent, right? We've never been trying to solve a math problem and suddenly found that we've reached 1 = 0 without us messing up, right? And then the second piece is that you can't prove consistency within your system, but you can prove using another system that your system is consistent. Unfortunately, at some point you have to stop, right? So the foundation of the consistency proof isn't necessarily there. And then there's a third case, actually. There are systems that are both complete and consistent. We'll talk about that at the end. So how do we prove Gödel's theorems? Well, what we need to do is first we need to formalize a proof, right? We need to talk about a proof using arithmetic only. So we need to convert from a formula or a proof to a number, because once we convert it to a number, then we can talk about that number using arithmetic. The second thing we need to do, once we've talked about this thing as a number, is we need to talk about using this number. We need this, once we can talk about proofs and formulas in terms of numbers, then we need to talk about provability, whether something can be proven in terms of numbers. That's the second piece. That's going to be, so the first piece is Gödel encodings. The second piece is the provability predicate, is how I've written it. And then the third piece is using this sentence about provability, get to the paradox that we talked about earlier. And that is going to be through diagonalization. You guys remember how we talked about Cantor's diagonal argument, and Gödel does a very, very similar argument in order to get to his paradox. And then after that, we can pretty quickly get to the first and second theorems. So let's start with encoding. We have all of these symbols here, right? And our end goal is to encode a proof or a formula as a number. So we should start small. If we've got a list of symbols, right, all of these true, false, not, we can number these symbols, right? We can number this 1, 2, 3, 4, and so on. We can make a list. There is a little bit of danger here. This might be an infinite list, right? We're not talking about one predicate. We're talking about an infinite number of predicates, P1, P2, and so on, right? And we're not talking about X. We're talking about X1, X2, and so on. We're not talking about one F. We're talking about F1, F2, and so on. But we know how to deal with this, right? All we do is we go, in our list, we order it X1, P1, F1, and then X2, P2, F2. And so what we've done is indexed. For any symbol that you give me, I will be able to tell you its index, right? So let's define that. I can erase this. So G of S is the index of S. Now the great thing about this is that it's reversible. Given the Gödel number, that's what that's called, by the way, G, the Gödel number is defined to be the index of S. So then the next question becomes, okay, so we can express a single symbol as a number. How do we express a formula, right? A string of symbols. Does anyone have any ideas? Product of their Gödel numbers. So we could do, for example, we could do 2 times, so if we had, for some reason, false and false, right? Then that would be 2 times 4 times 2, right? And that would get us, what, 16? Yeah. So in that case, though, I could write 2 times 8 times 1, right? And maybe say this one is 8 for some reason. In that case, I've just written the statement false or true, right? And I'd still get 16 as the Gödel number. That's the issue with this idea. It's close, certainly. But now we've got multiple formulae with the same Gödel number. So this is, go ahead.
Use the Gödel numbers to multiply some prime numbers.
Exactly. That's why we started with the uniqueness of prime factorization. Because then what we know is that if we set G of X, where That's going to be g of S1, S2, and so on to Sn. And if we define that to be 2 to the g of S1, right? G of S1 is computable, certainly. 3 to the g of S2, and so on to Pn to the g of Sn.
So is this kind of equivalent to, instead of indexing your symbols by 1, 2, 3, you index them by prime numbers?
Yes, I think, yeah, except this thing I think will nest a little bit better, I think. Because, yeah, you're right, if you multiply primes, you can probably recover the originals pretty nicely. You might not be able to recover order, whereas this can recover order.
Just a question. When we talk about arithmetic, we don't talk about irrational numbers because your list is countable, I assume.
Yeah.
Okay.
And it's countable because all of these predicates are indexed, all of these variables are indexed, and all of these functions are indexed.
Right, and there is like, they have the size of the integers.
Countable number of numbers. Yeah. So if we write it like this, then with our statements we can get this list of primes, and we'll get a number. It might be a very large number.
Do we know that the list of primes is countable, though?
Yes.
I think so, because it's part of the integers, right? Yeah. Cool. So, all right, we've got the Gödel number of a formula. So then here's the question. That's great, but we need to talk about proofs, not formulae. Well, we need to talk about proofs and formulae. How do we talk about proofs?
It's the same way we talk about arithmetic, right? But since we have a one-to-one correspondence between proofs and numbers.
Yeah, you're saying repeat the same trick, right? Yeah, exactly. So then we can say g of a proof, which is x1, x2, x3, and so on up to xp, for example. That is 2 to the g of x1. That's 3 to the g of x2, and so on up to, I shouldn't go with p, xm. So what have we done here? We have composed an entire proof into a single number. And we have chosen that number in such a way that we can go back, right? We get the prime factorization, and then we get each of these formulae in our proof. And then, because we've got the Gödel numbers of the formula, we can do this trick and get each symbol. And then once we have each symbol, we can reconstruct our entire proof from one number. And why is it important that it's one number? It's because we're talking about a formal system for arithmetic. And arithmetic is very good at handling one number. So this G, the Gödel number, is a very powerful tool. Man. Of course, one thing. So we're only talking about whether this number can be computed, is computable, not whether it's efficient to compute it, nor whether it's even reasonable to compute it. These are giant numbers, and very quickly, especially when you get to the very long proofs, right? There have been published in Nature, there have been 100-page proofs or something. Yeah, maybe don't do that on a computer. So now we're able to talk about these numbers. Since this is a number, we could write a mapping from one number to another, right? That's a very normal thing to do. Let's call this mapping, I can erase this. And this. Let's call it proof. So proof of two numbers, x and y, will represent the statement X is the Gödel number of a formula, of the proof of a formula with Gödel number y. This is a doable thing because x and y are both numbers. And so all we have constructed here is a mapping from one set of the numbers to themselves. However, this mapping that we've constructed talks about whether things are provable, right? This is where I start getting really excited. So in that case, we can ask the question, is y the Gödel number of a provable formula? Is that visible? Is it too low? Okay. So is y the Gödel number of a provable formula? Does anyone have an idea of how to write that? It's very simple. Does there exist an x such that proof of x, y? That's it. Provability, free in a line. And then we can ask, because of this, let's define some syntactic sugar. We can say P of a formula x is just PR of G of x. Right? So if I have a formula, then I can say P of x is just how I check if x is provable.
Does proof correspond to some unknown arithmetic operation?
I don't believe so. I think you're going to get into probably the halting problem type thing. Like you might be able to find a proof, but you might not have a terminating algorithm that finds the proof, or something along those lines. So we can write this statement, P of x, where given a formula x, this tells me if x is provable. And this is a formula that works completely within the bounds of arithmetic, right? It's not just a magical oracle. There's a little bit of an oracle, but it's an arithmetic oracle. So what do we know about this P of x, right? There's a couple nice things we've got by construction. I'm going to write that right here. So by construction, we know that theorems have proofs. That is, if P is a theorem, then sorry, I should use x. If x is a theorem, then, did I write that wrong? Yeah, I did. If x is a theorem, then the proof of x is a theorem, right? That's the definition of what a theorem is. Another thing we have is, if I can show you, so remember modus ponens, which is right here, right? If I can prove x implies y, then if I can prove x, then I can prove y, right? Actually here, if x implies y is a theorem, but the way I've said it just now, if I can prove, that is, I could write, oh, by the way, this is PT. So if I can prove that x implies y, then that means that, is that non-parentheses? Yeah. That the proof of x implies the proof of y. Right? It's just a restatement of modus ponens as we wrote. So we'll call this PMP. Now you might be wondering why I'm labeling all of these equations. It's because if we have time when we start actually proving Gödel's theorems, they're just a combination of these theorems, statements that we're writing over here. And if we don't have time, well, you guys have the URL and you can see it. So the last thing is that if you can prove something, then you can prove that you can prove something, right? So if you can prove something, then you can prove that you can prove something. That is, proofs have proofs. So I'll call that right? This is what our provability predicate gives us. Just some nice properties. So now let's do diagonalization. Suppose we had a list of all monadic predicates. That is, we have a list of all formulae with one free variable, right? Yeah, let's start here again. So let's say we've got this list, B1 of n, B2 of n. Let's make it down. And so on. You have BK of n, and so on. It just keeps going. Very long list, right? This can certainly exist. And we can also write the numbers. I should just do dot, dot, dot. Okay, so on. So here's a question. What type is P? P is a predicate taking a formula, right? It's certainly not on that list, right? But I could ask, what type is P BK of Bn of n? Is that readable, by the way? What type is this? P Bn of n. Sorry?
Is that taking like a statement that Gödel number is represented?
So P will, yeah, so it'll take this formula, Bn of n, and convert it to a Gödel number and then check if it's proved. So the key variable that's free is n, right? N is the only free variable here. That is, P of Bn of n is a predicate taking one integer. That is, it's somewhere in here, in our list. And specifically, what's it doing? Well, it's checking if the value n fits the nth predicate. That is, it's looking at this box, and so on, and it's looking at the kth box. Right? Hence, it's called diagonalization. Did you have a question? Okay. So this is a statement in our list of predicates, so we can write. So let's suppose that it's some BK, right? So BK is basically defined as P of Bn of n. Right? The one thing, if P of Bn of n is in this list, then so is not P of Bn of n, right? If I've got a predicate, the opposite of the predicate should also be in the list. So actually let BK be this statement. Sounds good? Now, actually I should write bk of n, right? Are there any restrictions on n? Can I choose any n I want? Okay. How about I choose k as my n? So then we write bk of k, if and only if, not p of bk of k. Well, that's a little weird looking. And just to make things clearer, let's just set a is equal to bk of k, right? So then what we've basically done is a, if and only if. Oh, by the way, this is the definition. And so therefore this is a theorem. And so therefore this is a theorem. Let's talk about what this says. It says that A is true if and only if not P of A is true. That is, A is true if A is not provable. It's the paradox we were looking for. That says this statement is not provable. So from there, effectively, we can begin the havoc. So I'm going to write that here and give it a label. How much time do I have? 15 minutes. Good. Not P of A. This is paradox. P dx. All right. So, first theorem. First theorem states that if, so actually we're going to start with a lemma. So this lemma it's a helper to the first incompleteness theorem. It says, given a consistent formal system containing arithmetic, you can write a formula that can be neither proved nor disproved. So how's that different from the first theorem? If I'm saying you can write a formula that can be neither proved nor disproved. The first theorem says you can write a true formula that can be neither proved nor disproved. They're very similar. In fact, we'll see how they go from one to another pretty
First
quickly.
theorem says that you can write a true formula that is not provable.
That is, can be neither proved nor disproved. That is, let's just write it. So, first theorem says that there is a statement C such that you can't prove C and you can't prove not C. Right? There is a true statement, C. That's the first one. So what we're going to do is just forget the true part for now. So, this is a little math heavy. So the first thing we need to note about our paradox, right? If we start with our paradox, A, if and only if, not P of A, right? Then from there, we can take the contrapositive, right? Swap them. P of A implies not A. It's the CP over there. And then we can, if this is a theorem, then it's got to have a proof. So we can say that there's a proof of it. Are you guys following? I won't be looking at you guys very much while I'm writing this. So.
Is there a reason we dropped the if and only if?
Not necessary. so feel free to shout at me. And the next piece is, well, if this thing is provable, then we can do, this is an implication, right? And so we can do modus ponens, or so P of, P of A implies P of not A, right? And that's PMP over there, right? And then, well, P of A, well, we know P of X implies P of X, right? So we've got P of X implies P of X, and then P of X implies P of not A. So basically, P of A implies P of not A. And this is the combination of the fact that things are provable, that proofs are provable, and also this, what's it called? Syllogisms, hypothetical syllogism. We follow this? Yeah? Not exactly. You need to have one of these to be true, right? If P of A isn't a theorem, then we can't have this theorem. That's inconsistent. So, what does it take for P of A to be a theorem? Well, this thing, right? So the first theorem is proven just by taking this A. If A holds, then we know P of A holds from PT. Theorems have proofs, right? And then from this, we know that if P of A holds and P of A implies P of not A holds, then we know P of not A holds. And that's a contradiction. Okay, so maybe A doesn't hold, right? Maybe instead not A holds, right? A can be disproven. Well, then in that case, we can do the contrapositive of the paradox. So our paradox was A implies not P of A, right? Or if and only if not P of A. Well, then if we take the contrapositive, then not A, if and only if P of A. So from not A, we can prove P of A. And if we can prove P of A, then we can prove P of not A. And we're in trouble again. So therefore, we can't say this, and we can't say this. That is, we've got a statement C such that not C, such that C isn't a theorem and not C isn't a theorem either. A statement that can't be proven or disproven. There's one piece missing, right? What's that one piece? Whether C is true. However, we know that either C is true or not C is true. And neither of them is provable. And therefore, we just pick the one that is true. And so that C, or not C, whichever one is true, is a true statement such that it can't be proven or disproven. That's the first incompleteness theorem. Given a system containing arithmetic, you can write a statement that can't be proven or disproven. And it's just arithmetic. That's all we've been using. And logic. But still. So let's do the second one, right? Second one also follows a similar chain. Right. I'm going to keep one of these statements. I'm going to keep P of A implies P of not A. and I can call that P PDX. PF PDX. So now I can erase this. And we're going to start, first off, so the second theorem. You guys remember the second theorem?
Statement C such that not C.
Yeah, second theorem says that you cannot prove consistency. Well, what does that mean? Well, what does it mean for something to be inconsistent? If it's inconsistent, then there's a proof that 1 equals 0, right? So when we say that something's consistent, then there's a proof that there is no proof that 1 equals 0, right? It's not possible to prove 1 equals 0. And this is true for any consistent system. However, if you can prove that it's consistent, then we know that this is a theorem, right? So this is the assumption we're making, and we're saying that this cannot hold. We'll get back to that. First, we're going to do another little bit of a wandering. We're going to note, using our trivial implication, right, P, that if A holds, then that implies that not A implies 1 equals 0. Right? So then we know that P of A implies not of A implies 1 equals 0. And this is TI. This is theorems have proofs. And then from this, we can split it up, right? Modus ponens again. P of A implies P of not A implies 1 equals 0. Right? That's PMP. Right? And I'm going to start erasing here. All right. Let's keep going. Okay. So if I can prove A, then I can prove not A implies 1 equals 0. Right? Then I can do PMP again and say that P of A implies, are we still following? Okay. P of not A implies P of 0 equals 1. Right? And this is another modus ponens. I just split this one up. And then from that, well, P of A implies P of not A. So let's do the, what's it called? This, distributing the implication. So that's P of A implies P of not A, implies P of A implies P of 0 equals 1. This is implication distribution. So, does this look familiar to you guys? We've proven that. So if we've proven that this holds, and then we prove this implication, well, then that tells us that P of A implies P of 0 equals 1. That is, if we can prove A, then we can prove 0 equals 1. All right, so we said assume not of 0 equals 1, right? So not of 0 equals 1, if we go from that, well, then let's do contrapositive, right? So this holds, and then the contrapositive of this is not of this implies not of this, right? So we know from that that we have not of P of A. not of P of A, though, we can use our paradox here. Not of P of A means we know A. And if we know A, then we know P of A. And if we know P of A, we know this. So if we assume the system is consistent, we just prove that it's inconsistent. So we can never have a system that proves that it's consistent. It would immediately fail. And that's Gödel's second proof. It's awesome. So, last thing, did we just break math, right? That's a very important question to ask. And the answer is that no, we didn't. What we have shown is that there are things you cannot prove or disprove. We have not gotten any contradictions, right? And one of the things we can't prove or disprove is that a system is consistent within itself. But at the same time, you need this, like all of these constructions of arithmetic, which means there are exceptions. So for example, a guy named Alfred Tarski, a Russian mathematician, I think. Sounds Russian. Tarski showed that the real numbers are analytic geometry, so the theory of real fields, is both complete and consistent. And if you guys look for his proof, then you'll be able to find that. And there's other things like, there are a couple more examples of this, the continuum hypothesis we talked about, right? And there's also that you can use other proof systems. And if you can use other proof systems, well, so the same problem of whether the Peano axioms are consistent was actually proved to be true by a guy named Gensen. And Gensen did this by using another proof system. And so he argued, actually, the proof system that Gensen used was simpler than the Peano axioms. So you don't even need to use a more complex proof system. So you could get some very simple, very close to obvious proof systems. And of course, there are systems like Pressburger arithmetic with divisibility, which are just consistent. And not only are they consistent, and they're also complete, and also they're decidable. That is, you can write Turing machine, not Turing, you can write automata that will decide them. So they are even simpler than Peano arithmetic. You can get even better results. So mathematics is still awesome. You should keep doing it. Yeah, that's everything.